get underway, shall we? Master Math asked us to count you twice, so I'll let this one go round again. Put your name there. So what's the plan for today? Well, today we'll do the axiomatization properly. Well, maybe today and next week, because I discovered that there is lots of stuff to do when you go through the axioms, so step by step. I think we'll get to the Cartesian product today. But before we start, are there any questions about the homework? Not the homework, the exercises. The homework will be today. Yeah.
Was there a way to do question 1 without appealing to foundation or power set?
What was the one problem? I forgot what I asked.
Show that every set X has a subset that is not a member of X.
No.
There was no way to do it.
You don't need anything other than separation.
Okay.
And Russell's paradox. I'll give it away, shall I?
You actually gave it away during the lecture.
Of course I did. That's as short as I can make it. But the history is a little bit different. First, there was Cantor's result that, well, no, if you read the paper properly, you will find that he proves for the natural numbers that there are more sequences of zeros and ones than there are natural numbers. And then he proves that there are more functions from the unit interval to the 2-point set than there are numbers in the unit interval. That's everything that's proven in that particular paper. Russell turned that into this, for example, and also into a proof that for every set, the power set is strictly bigger. Because you prove without any ado that this particular set that depends on the function f is not in the range of f. And all we are doing here is take the identity function, actually. So this is what Russell extracted from, well, I guess many people saw through Cantor's proof and saw this idea that you can get ever larger cardinal numbers in this way. Actually, Cantor himself saw that, but Russell, in the paper that I put on the ELO last week, he gives this example. Not as short as this, but with words like X being related to a subset of X and everything. But this is the whole thing in symbols. And then he started to talk about this thing that we talked about last week. Can we take an arbitrary formula and turn it into a set? And he said, no. So from this idea, he went to the set of all sets and then derived the contradiction. But I tend to say that every good paradox is also a good theorem. So Russell's paradox is actually a theorem that says this set of all sets doesn't exist, and it is this homework exercise as well. Or exercise. And as you can see, you don't need any foundational thing whatsoever. Any other questions about the exercises? Anybody able to follow in Dedekind's footsteps and define addition? On his smallest set that contained the 1 point and was closed under the function f. Because, so we had this set This was Dedekind's version of the natural numbers. In the paper that I talked about, he was really trying to found the theory of the natural numbers just in sets. And so he needed something that would behave like the natural numbers, and this is it. And, well, let me, so before, this was really a trick question because you need to you need to do some preparations before you can really start to work on it. The point is the x is going to play the role of the 0, right? That's what I said last week. And before you can start to define addition, you have to prove and discover a few properties of n that make it look more and more like the natural numbers that we know and love. Well, not x, because let's call it x0. So we have a variable x again. So if x is in n, for example, you have to show this before you, in the course of checking that your definition of addition is going to be correct, you need, for example, this fact. Now, why is that? Well, the set of all x's with this property is a subset of n. It contains x0, and it is closed under this map. Therefore, it is equal to n, because n is the smallest set with that property. And that's the argument that keeps on returning. You have to prove something about all the x's. Well, take the set of all the x's with the property and show that it satisfies this. Well, usually x0 is there explicitly or something, and show that it satisfies this. So then it's the whole set n. It's like proving stuff by induction. It is proving stuff by induction, because f of n is going to be n plus 1. So if x0 is going to be 0, then f of x0 is going to play the role of 1. And there are a few other things that you have to check here. For example, you would want to order these points in n. That somehow is a little bit harder than I thought at the beginning. Oh, easy. But you can do it in a tricky way. Yeah, that's right. You can define, why not, a of x0 to be empty. And you can define a of f of x to be a of x union, say, singleton x. The set of all members of n for which this is for which a of x is defined satisfies the properties of n, so it is the whole of n. This defines a function on that set n. And then you can order the set n by saying x is less than y if a of x is a subset of a of y. Oh, we have an order. Fine, lovely. Then you can prove that the order is a well order. How? Well, you prove that every ax is well ordered, and from that you deduce that the whole set is well ordered. And then again, ax is well ordered is a property that is preserved by these two things. Therefore, all the members of n satisfy it. And you keep churning that thing, and all the results that you would like to have drop out. And then in the end, you simply define the addition by recursion. You simply say, well, x0 is going to be 0, so by definition, x plus x0 is going to be x. So what is f of x plus x0 going to be? Well, it's going to be the f of x plus x0 because we want it to be plus 1. We want this to say x plus 1 plus x0 is x plus x0 plus 1. And maybe you should flip them around, actually.
I think it should be f of x plus x, f of y plus x.
Pardon?
You cannot write x as 0 both there because otherwise it's simply.
It does not.
Oh, sorry, that's going to be a theorem.
Yes. I think it's f of y plus x.
Depends. I think you can get away with both directions, but we'll get to the real definition and the real natural numbers eventually. But let's see, f of x.
This does not define this. This is not the full recursion, right? Because
Okay, you mean?
yes.
I think maybe I already had it, but this is okay. This is it. Y plus x0 is going to be y. Y plus f of x is going to be f of y plus x. Certainly this works. Thanks. And then you can prove that this is commutative, associative, and whatnot every time doing this by induction. Every time you say, well, take the set of all the members of y of n for which y plus x0 is x0 plus y. It's going to be the whole set because it satisfies the properties. Yo.
What would be wrong with just going straight for the definition by recursion without having yet done the order and so on?
Okay, this particular thing doesn't need the order, right? Although, if you want to show that it's well defined, you at least need this. Because, you know, y plus x0 needs to be defined. Well, how can I define, how do I know that y plus x is defined for all x? Then I need to know, okay, that's unfortunate, there is a y there, but that x is the f of a z. And then go back to, oh, we knew what y plus z was, and then we can put y plus x in there. So this is certainly needed. I think the well order you can postpone until you have addition, but
you wanted to show.
But we want to show that we have the natural numbers, so the well ordering has to be proven eventually anyway. The order Okay, that can be your own preference, but as long as it's logical. So that's how you, if anybody has seen the development of piano arithmetic, this is what you have seen there. And piano arithmetic ultimately comes from Dedekind's attempts to define the natural numbers. Some people call them the piano-Dedekind axioms, because Dedekind did the whole thing in that paper that he maybe published just a little bit after Peano did it. I forgot the years. Any other questions?
Do you need well-foundedness of your... because you can define something inductively, but if you never reach your like constant adding with 0, then we never...
Well, the well-foundedness is the well-ordering that I just mentioned.
Yeah, fair enough.
But if you want to say, show that y plus x is defined for all x, then you can get away with just this. Because using this, you can show that the x's for which y plus x is defined satisfy this property. And you don't need well-foundedness in the sense that there are also non-standard models for arithmetic, which on the set theoretic level are not well ordered, but on the piano arithmetic level are well ordered, because you only look at definable subsets there. So then, then you get the non-standard extension of the addition and everything. So you have that well-foundedness, but for definable sets. And then the set of all x's for which this is defined is a definable set. So you have this well-ordered there implicitly.
Okay, in this way you show that addition is well-defined for every x. But is it not possible? Is it possible that in that definition you can define the addition for two different f of x in the same time? So f of x is reached by this different y safe in...
I guess so. I never tried it because I slavishly followed the books when I did that kind of thing. Okay, so the theorem now is that we fixed a y and we showed how to define this addition. And so now we can put a universal quantifier in front of the y and say for every y and for every x we have defined the sum. Using only one instance of f makes life a little bit easier. Because if you want to, so you would like to say f of y plus f of x, but you also have to look at f of x, sorry, we have y plus x, okay, that's the given. Then we can define y plus f of x. And we could conceivably define f of y plus f of x. But the way I've set it up is that I first fix my y and define all the additions with the second one variable. So I fix the y and then I define y plus x for every element of n. So okay, that's a good definition. Oh, I did it for all the y's. So the addition is a union of functions, one for each y. And yeah, that makes, and then you have to, like I said, you want to prove that all the normal rules of arithmetic hold. And yeah, well, it'll take you a few pieces of scratch paper to do all that, because I've seen it done in a few books and it goes on for forever, almost forever. But it works. And it's a good exercise to get the feeling for what the inductive thing does. And why not try for yourself to see if you can get it for both at the same time. I'd be interested to see if there is a relatively transparent solution to that. Okay, anything else that I gave to you? Okay, and there were some exercises where you had to write down precisely some of the things. I guess everybody could do that. All right. Okay, here's the... Okay, so last time we basically did Zermelo's axioms, and then I said next week we're going to do it properly. So what do I mean by properly? Well, what I hinted at last week was that Zermelo's idea of definite, it sounded okay, but many people said, not precise enough. And so two people, Frenkel and Skolem, had an idea. And we have adopted Skolem's definition, but in what Frenkel suggested, also it has a little bit of merit, a little merit that we will discover later in the course. This is what Frenkel had to say. I copied a quote from the paper in the notes, and you will see that tonight when I scan them. He wanted to use functions to describe what was going on in Axiom 3, right? Axiom 3 had the definite property thing. And so a definite property of X would always be something of this nature. You had two functions implicit in the axioms. So he had count the braces. This is the example that Frenkel wrote in his paper. Okay, but this is implicit in the axioms because the empty set was postulated explicitly. We would be able to take the singleton set that contains the empty set. We would be able to create the singleton set that contains X itself and the singleton set of that again, and we are able, I think, I need it, yeah. I think now everything is in balance. So this one, that's the first thing. And then we simply take the union of the power set and twice singleton empty set. And then we stick that in an unordered pair. Okay, well, that certainly that's an example of a function, but how useful it is, I'm not quite sure. But I think he just wanted to show how complicated or how silly it could be. Anyway, there are, of course, more better usable things, but this is not too bad, except that it has these finite combinations of functions implicit in the axioms in it. And he also tried to use functions that come from the axiom of choice somehow. I read it and it wasn't quite clear to me what he was on about, so I'm not even going to try to repeat that. But anyway, this is what Frankel did. And as you will see, this didn't make it. Except that we will meet this idea again when we're looking at the constructible universe. The way Gödel constructed the constructible universe was using finite combinations of functions almost implicit in the axioms. Not the power set, that was a bit too much, but a bit simpler. So we'll get back to this idea eventually. So, well, if that was Frankel, what did Skolem do? Well, Skolem wrote we use the 5 basic operations of logic. And what are those? Well, he was making a list of 3, and you will see why in a moment. I'm not writing any symbols just yet. Because, okay, this is not how Skolem wrote this, and I'm using our modern symbols. Skolem used a dot, a plus, a bar over the formula. That was the idea in those days. And capital pi and capital sigma as the quantifiers. And of course we do these symbols now. And why there is only 3 things? Well, you can express one of the ones in the other with the negation in it, and you can express one of the quantifiers in the other one using the negations. At least if you do classical logic. If you do intuitionistic logic, you cannot. But we're doing classical logic here. I like the excluded middle. Makes life much easier. So anyway, we can, using, say, just and, not, and for all, we can write down everything we want, logically speaking. Okay, but where do we start? We start with atomic formulas, where we can take we can use as many variables as we want, but everything of the form x element y, u element v, whatever. and x equal y, u equal v, and so on. All those things are our starting formulas, and then we build up formulas using these operations. And remember, I wrote something like this last week when I expressed axiom 3 of Zermelo. Now we know what the fx is going to be for us. It's going to be from the set of well-formed formulas that we create using this. And I think anybody who's done a course in mathematical logic, well-formed formula is one of the first things that you see. Okay, and that's it. And that is what we still do. Okay, on the ELO website, there is a link to chapter 1 of Jech's book on my computer. If you study that URL closely, you'll be able to get way more than that. You will even be able to get this. But you have to scroll down, way down. What I'm doing is sort of borrowing both from Jech's book and from Koenen's book. And I'm going to use the enumeration of Koenen of the axioms because it was on my table when I was preparing it. And I'll give you the numbers of Jech's book as well, although once you see the axioms, you can find the numbers yourselves. And so, just to be absolutely clear, when we do a first order theory, we need a language. And I'm going to make the language really redundant. Yeah, those two parentheses. Because to make things precise, we need parentheses. Although, if I was really good at it, I could use reverse Polish notation, and then everybody would be busy. What the hell is he writing now? It can be, that's without parentheses, and it's uniquely decodable, but the decoding is a little bit awkward. So these are the logical symbols. These are the symbols specific to our language, although sometimes this is already part of the logical language, right? This particular predicate. Okay. Oh. And we have variables that are indexed by the natural numbers. And we don't have natural numbers. Yes, we do, we don't. I think last time somebody came to ask me about this after class. We are doing, in this case, set theory on two levels. The meta level and the level of first order logic. What I'll be trying to convince you of in the first part of the course is that this first order approach allows us to do what we normally do, just naively, so to speak, on that first order level. And when we say that something is provable, we mean that it is provable in the sense of first order logic using those formal derivations. And then we always say, yes, but every proof that we write down could be written down as one of those formal proofs. Nobody ever did that, but of course, just for showing that the intersection exists and the set theoretic difference and stuff like that. But nobody has really taken the proof that the axiom of choice implies the well-ordering theorem and turn it into a finite formal derivation. That would be a good exercise, but it would also be tedious. Anyway, so we have, when I say indexed by the natural numbers, I'll get back to you in a moment. When I say indexed by the natural numbers, it's those natural numbers on our own level, the natural numbers that we grew up with, so to speak. Because there is no way, for example, thanks to Gödel's incompleteness theorems, to close that circle. You can found logic and you can found logic in set theory. You can found set theory in logic. So you can found logic in set theory, you can found set theory in logic, and you just keep on going. That vicious circle cannot be broken. At one point, you have to say, well, okay, we are doing mathematics in the normal way that we always do. And we talk about what we can do using those formal derivations in first order logic. Because after a while, you will see me do normal mathematics when I'm doing the set theory bit, rather than formal derivations. But in the beginning, I will be really trying very hard to convince you that all the things that we know can be constructed in that first order situation.
Yes. So like you said, there was a problem with using the natural numbers to index them, but we don't need to give them meaning. They're just symbols, right?
Yeah. But if we want to write down stuff, we need infinitely many of them. And any normal alphabet is exhausted after finitely many steps.
Use ticks. Ticks have really long.
No, it was kind of simple.
Yeah. Yeah, and although our variables are all called v and all have an index of natural numbers, first order logic tells you that all the other alphabets are fine as well. When you take a variable and replace it everywhere by another one, you don't change the meaning of the formula. Given one or two, keeping in mind one or two rules that you don't get into the scope of another quantifier and everything. But if you don't do anything silly, you can use all kinds of variables at will.
A question. When I was talking to some people in the rudiments course, they, for a problem, needed to use the fact that normally in first order logic, when you quantify, you assume you have a non-empty domain.
Right.
Are we making any such assumptions when we found ourselves in logic right now? The domain we're quantifying over is non-empty.
As you will see, there is an axiom 0 in a moment.
Yeah, but we need that.
Yeah.
Yeah.
Or we don't.
True.
By the excluded middle, yeah. Because there is a pure existential statement among the axioms. The infinity axiom. It says there is something, and you can keep away from that for a while until you introduce the axiom, and you say, oh, suddenly, hey, we have sets. I'm not going to do that. So what am I going to do? Oh, yeah.
Why do we need any special existence axiom? There's an exercise x equals x, isn't that a theory of first order logic?
Well, that depends on your first order logic. The book that I learned it from, Mendelssohn, has at least a section on quantifying over empty domains. So he said, well, you know, we always implicitly assume that our models have elements, but what happens if we don't have anything? So, and if you don't have a theory with equality, there's no way you can declare the existence of any individual other than by giving a constant for the language. Especially if you don't have any predicates either. Usually we have a predicate and then you can say, okay, there is an x such that predicate xx or something like that. Which is bad if you want the predicate to be a strict order. So then you don't. And so actually, non-empty domains, the safest is to have a theory with equality there. But, okay. Well-formed formulas are formed as you have come to expect. Really, so and officially, whenever we have one of those binary things, we put parentheses around the arguments to make it unambiguous. And so also, if we put the negation in front of it, and I'm very careful, I even do this. Koenen's book there occasionally drops these, but I really, really want to be unambiguous. So, official formulas are, of course, the V's with indices from our natural numbers, whatever they may be. Everybody knows what free and bound variables are? Okay, fine. Bound. X is bound. This Y is free. This Y is bound, and this Z is free in the whole formula. So Y is free only in the first bit, and Z is free everywhere. Well, it doesn't even occur here, but Y can be free and bound at the same time in the formula. That kind of thing can happen, and that's what I meant. You know, if you don't really like that, you say, well, this could be a number or whatever. Okay. Take a fresh letter, a fresh variable, stick it in there, and then you don't have any problems and everything. Your bookkeeping is a little bit more sound. And logic tells you, yeah, that's okay. So that's that. And the point is, for free variables, you can substitute values. For bound variables, you cannot.
I don't see phi and psi in our language.
Pardon?
We're using phi and psi, but they are not in our language.
Those are meta variables. If phi is a well-formed formula, then so is this. If, then so is this, then so is this, then so is this. Those are the production rules. Very good. And so, this is Axiom 0 from Koenen's book. And he makes the remark that some logic books dictate that there is something, and then we don't need this, and he just says, I'll do it for definiteness. So at least we have something to play with. And axiom 1 we already know. That's the extensionality axiom from Zermelo, but okay. Yeah. Okay, two things are happening here. I'm not as strict as I said I would be with those parentheses. Because obviously this is an atomic formula, it cannot be broken. You could never ever read this as arrow x is equal to y. It just means we have this thing here, and it implies that atomic formula. So we do like to keep our things a little bit sane. And of course, here is d for every x, d for every y. Now, it depends again on your book on logic. This is usually taken to be a logical axiom. So if you say, well, if x is equal to y, do we get this? Yes, we get this from the logical axioms that we set up. Because you will have seen in your logic courses that every theory has a bunch of logical axioms. Those are always the same. And then the proper axioms of the theory. And the other one tends to get put into the standard logical axioms that we use all the time.
Since you say the converse belongs to the logical axiom, but that sentence contains a symbol of our own particular language, the epsilon belonging. So it belongs to our language, not the logical.
Sure, but the logic, like I said, some books simply say, well, if x is equal to y, then for every formula, when I replace x by y at certain, then those things become equivalent. And that's a whole axiom scheme, actually. That's one thing. The other thing, the second version of Kunin's book that I'm not quite sure if it's sort of available. It should be available printing on demand. The other book has these explicitly in the list of axioms, this kind of thing. Why? Well, there are lots of theorems, for example, in Mendelssohn's book, that if you have this idea for atomic formulas, then you're there. Then you can prove it by induction for all the formulas in your language. So you can say, if x is equal to y, then formula for x implies formula for y when you replace some of the free occurrences of x by y. And that's exactly what I did. And I can even put for every z in there, x and y are free, and what the axiom says is that if you do this, then that's okay. But the quantifier is not even necessary, because the generalization rule will let you do that. So there are lots of tiny things in your particular logic courses that make this easier or harder. And I'm taking the easy way out by saying, well, that other direction is given. But if in a pinch, we could actually prove it from very simple instances of those axioms. Well, it's time to have a break, I think. So in this case, we did it the other way around. We had some question and answers, and then I did some lectures, and I'll lecture, and then we'll have some questions and answers later. So let's take 15 minutes.